2.8 is our last section in chapter 2. This one is called the mean value theorem. And a preliminary theorem to that is actually Raleigh's theorem. So Raleigh's theorem says the following. If you have a continuous and differentiable function, so it's continuous on the interval AB with the endpoints included, differentiable without the endpoints, and the function at A, the function value at A equals the function value at B, then there is a number somewhere between A and B where the derivative is 0. So if you sort of imagine the picture going on, get a line tool. I know, it's because there's a line tool. Isn't that great? I wouldn't be so good at it. So imagine that you've got something that looks like this. And at the endpoints, they have the same y value. So this is the same y value, whatever it is. This is A, and this is B. So at the endpoints, they match, at least the endpoints of the interval you're looking at. All this theorem is telling you is that somewhere between A and B, your derivative is 0. What does it mean to have a derivative of 0 visually? Tangent line is the slope of it's 0, and the tangent line is, what were you saying? Were we, Kathy? Horizontal, right? It's a flat line. So we've got a horizontal tangent line. Can you see where it is on the picture that I've drawn?
Yeah.
Well, sure. And we've also talked about, not always, but often, when we have that tangent line where the slope is 0, that we have a maximum or a minimum value, right? And you definitely see on this one it's a maximum. So right up here, this is what Raleigh's theorem is ensuring us will happen, is that right here somewhere in between, we'll call that point C, that there's a location that's not drawn very well, but there's a location where the tangent line is flat. It's horizontal, the slope is 0. And it doesn't have to be just one location. The picture could actually look something like this even. So notice at, we'll use this point and this point. Those are roughly the same y value, yeah?
Yeah.
So let's call this point A, and we'll call this point B. Somewhere between A and B, do I have horizontal tangent lines? Yeah, I actually have 2. So this theorem doesn't tell us there's only one, it tells us that at least one happens. So there's actually 2 places on this one. So this one we could call sort of C subscript 1, and this one could be called C subscript 2. And there's 2 spots where this is actually going to happen. So this seems sort of obvious, right? Seems like a reasonable assessment to make that, and we saw something sort of like this happen before. It was called the intermediate value theorem. Do you guys remember the problem you did about the car on the slope of a hill, and the idea that when you were moving forward you had a positive speed, I guess, or whatever, and if you sort of thought about moving backwards, you could call that a negative velocity, which means that somewhere in between the velocity was 0. This is akin to that. Even more akin to that is the next one. So the next one's called the mean value theorem, and it looks much more complicated, but it's actually just a more general statement than the one we just had. So again, notice you've got continuous and differentiable. If those pieces fail, then we can't do this. It's continuous and differentiable. Notice what you don't have. You don't have that f of A and f of B have to be the same. That's different than in the last theorem. But what you do see over here is you see that you're finding a C value between A and B, where the derivative does something over here. Can you recognize what this f of B minus f of A over B minus A is? What is that? That's the slope, right? The slope between point A and point B, right? This is just, all this is over here is this is the slope between x equals A and x equals B. So I know that I don't have sort of space on your paper underneath this. I don't think I did. Maybe I did. Did I leave it there? A little bit. Okay. So we're going to draw another picture, and I'm going to show you what this sort of looks like. So this picture doesn't really have to have the endpoints matching. So if I draw my picture the same way I did before, I'm just going to take my endpoint here, the first spot, and we'll put the other one right here. They don't have to match for this to work. Then if I were to find the line between these two, we could sort of visually imagine what the slope then would look like, right? It's a positive slope between them. That there will be some point over here C where the tangent line has that same slope. That's what the mean value theorem says. And do you remember, it was an example I gave verbally in class. I didn't have equations or anything to do with it. Do you remember the example I gave you of the police officer checking your speed and being able to tell that you were in fact speeding at some point? That's actually a direct application of the mean value theorem, which is an extension of the intermediate value theorem that we talked about a couple months or a month ago or so. So this is what's going on here. Now, if you take a look, what happens in this equation over here if f of b and f of a are the same? What happens if they're the same? You get a 0 on top, right? So you'd have 0 over whatever. They wouldn't be the same on bottom, it'd be 0 on the top. So you'd actually have to f prime equals 0, right? You'd have this statement over here. Okay? So Raleigh's theorem is actually just a very specific case of the mean value theorem. It's the case where the endpoints match. So you got that slope of 0, which would be a flat tangent line or a horizontal tangent line. But for some reason, it makes a lot more sense to us to start with Raleigh's theorem and visually picture what's going on, I think, than to actually start with the mean value theorem and say, oh, look, there's just one application. What happens if we have the tops the same? So they are applications of one another or different variations of the same thing. We're going to take a look at doing some examples with these. The first example tells us that we're going to check the hypothesis of Raleigh's theorem and the mean value theorem, because the hypothesis will tell you which theorem you're using. That's the kicker, all right? And we're going to find a value C that makes the conclusions true. And we're going to illustrate the conclusion with a graph. So we're going to draw a picture when we're done. All right, so there's a lot of things going on here. The first thing it says to do, though, is to check the hypotheses. So take a look back at these. What are the hypotheses that have to be true for these to work? Continuous, differentiable. That's in both of them, right? So we're definitely going to have to check that. What's the third thing that we're going to check to decide which theorem we're talking about?
If A and B, the locations of A and B.
Yeah.
Or the Y.
So if the y value is the same at locations at the endpoints, okay? So there's three things we're always going to be checking here. The first thing to check is it continuous, is it differentiable? So let's just visually talk about continuous and differentiable here. We get these almost for free. Do you know why on this particular one? Is a what? What's the equation? It's a parabola. It's a polynomial generally, right? And when we did we had theorem back before that talked about polynomial equations. Polynomial equations are continuous everywhere and differentiable everywhere. So we get these for free, and the reason we do is because it's a polynomial. And I'm just going to do those little things there that say that's the same reason for the differentiable part. It's continuous everywhere, it's differentiable everywhere, and that's because it's a polynomial. So we don't really have to do much to get that, but you do need to state it, because if you don't state it, then I'm going to assume that you forgot to look to find out if it actually worked. I know, it's so mean. I'm a terribly mean professor. All right, so you're just going to write down it's continuous, it's differentiable. I checked it. I visually looked, or some kind of a description of why this actually works. All right, the other thing we were supposed to do then is to check what happens at the endpoints, right, Mandy? Okay, so the endpoints that we are given are right here, x equals -2 and x equals 2. So we're going to check f of -2 and f of 2. And you don't actually have to show me the plugged in pieces, although you can if it's helpful to you to see them. But I really want to know what is the outcome here. All right, so what is f of -2? 5. What is f of 2? 5. So which theorem is this going to actually most cleanly fit? This is Raleigh's theorem. So we're actually going to be able to use Raleigh's theorem. And I know that's just a special case of the mean value theorem, but Raleigh's theorem is where this actually fits in most specifically. All right, so this says, well, let's look back to Raleigh's theorem so we can see what it says. It says if we have all these conditions at the beginning, we've checked that we do, all three of them, then there is a number where the derivative equals 0, right? In other words, we should be able to take this equation, find its derivative, and find out where the derivative is equal to 0. So that's what we're going to do. We're going to take this equation, and after all the fun and exciting equations you've been dealing with recently, this one is not fun nor exciting. What is the derivative of this one? Wow, my goodness,
I would
yes
say
it
it's
is.
pretty good to have one that's not.
That's a good one to not have. Okay, all right. So we've got the derivative. We're supposed to be able to say that this equals 0. So where does it equal 0? At 0. Yes, it does. Okay. All right, so let's go back to Raleigh's theorem. So it says then there's a number c, and our number is 0 between a and b, and our a and b was -2 and 2, right? So that works. Promise I'm on a different screen. Okay, so x equals 0. C equals 0 if you want to use the notation they had before, and 0 is between -2 and 2. Did they use parentheses or brackets? I think they used parentheses, yeah. So I probably should too. Okay, so we found the value of C. C was 2. I'm sorry, C was 0 between -2 and 2. And it says then to illustrate the conclusion with a graph. So hopefully you remember what this graph looks like. If you're not sure, you can use your calculator. I'm not going to scream at you or anything. But someone who is maybe a little bit sure, do you remember what this picture looks like? I know Ben already gave us one visual. You called it a parabola. And it's shifted up 1 because of the +1 at the end. Good. So it looks something like this, rough sketch, right? It does say we're going to do a sketch. We don't have to actually draw a specific exact graph, but this would be the sketch. And the sketch, actually, I didn't draw it quite so well. It's supposed to only go from -2 to 2, right? And what it's telling me from Raleigh's theorem is that I do have a place where my derivative is then 0. And do you see that place? Yeah. It's down here, right? It's not drawn very well, but you can pretend. Right there, at x equals 0 at the bottom, I've got a horizontal tangent line. So this is the graph that's verifying that we've done what we said we were going to do.
So if
All right.
you end up with something that's like going through the graph, you're probably.
It isn't so much the going through the graph, it's that it's not a tangent line for the graph.
Right, so if it's like.
And most of the time that would look like it's going through. Yeah, so if it looks just like it's sort of cutting through at a funny space, like if you had looked at this and it had given you the point, this. Let's say that this had been the point that came up when you solved this for an x, right at the very, over here on the f prime. Surely you should look at that and say, that does not have a slope of 0. I've made a mistake. So yes, that's what you would be doing at that point. Mm-hmm. All right, let's take a look at, yes.
Real fast, it was Raleigh's theorem that says the 5 equaled the 5.
Yes, that's exactly right. You'll be able to tell if it's Raleigh's theorem because Raleigh's theorem makes the two function values equal. Mm-hmm. Yeah. Thanks. All right, same example, or same, directions, different example. Directions in number, or the equation in number 2 says f of x equals sine of x, and the interval that I'm looking at is from 0 to pi half. All right, so what are the first two things that you're going to check? Yeah, continuity and differentiability. All right, so why in the world is this thing continuous and differentiable? It better be, otherwise I can't do anything else in the problem. Because it's a sine function, and we had a theorem about sine functions as well. Sines and cosines, those were the two that we had theorems about. So this is continuous, this is a differentiable function, it's because it's a sine curve.
What is differential?
Can take the derivative. You're able to take the derivative everywhere. And it really has to only be everywhere on that interval. However, for polynomials and for sine and cosine curves, they're actually continuous and differentiable everywhere, which means the interval doesn't make any difference. So we could have a graph that is discontinuous. So like take a look, think about tangent graphs. You guys know what tangent graphs look like, right? Got asymptotes everywhere. Agreed? Definitely not continuous everywhere, and definitely not differentiable everywhere because of those asymptotes. However, if you take your interval small enough, could you have a portion of the interval where it's continuous and differentiable? Yes, you could. You just have to avoid the asymptotes. Are you guys with me? So the ones that we've looked at, both on the last example and this one, it didn't matter what the interval was. But if the interval were different, we could actually have some of these other functions as well. Okay, so we get continuous and differentiable everywhere on this one. So what's our next step then? Right. Plug in the endpoints into our function. So we're going to try f of 0, and we're going to try f of pi halves. So I need to know what is the sign of 0 and what is the sign of pi halves. So sign of 0 is the one that's 0, and sign of pi halves is 1. So is this the mean value theorem, or is it Raleigh's theorem? This is the mean value theorem because they don't match. So the mean value theorem says, and let's go back to take a look at that slide, if the screen will let me. The mean value theorem says that we have a slope that we're able to calculate, right? F of b minus f of a over b minus a. All right, so you see the part in blue over there that says slope between x equals a and x equals b, that part? All right, that piece over there is what we're going to actually be able to work with. So we found the f of b and the f of a, right? That was the two sign values we just found, 1 and 0. And we know the b and the a on the bottom because those are the two x values we were originally given. So let's write this in first. We need to figure out what is f of b minus f of a over b minus a for our function. So f of b is the second sign value, that would be 1. F of a would be my first sign value. And then the x values, this is equal to 1 before, the x values were the original ones we were given right here. So the second x value was pi halves and the first one was 0. All right, so this is actually 1 over pi halves, which is the same as 2 over pi. I know we're not used to seeing pi in the denominator working with trig, but it's okay. So this is the slope, right? We have somewhere between 0 and pi halves, there is a slope of 2 over pi. We just have to figure out where, right? So back on that previous screen, it actually told us that we're looking now for the derivative, the location of the derivative to have that value. So I actually should probably find out what in the world the derivative is, I think. So what in the world is f prime of x for our function? It is cosine of x. So what we're supposed to then be able to actually find is where in the world is cosine of x equal to 2 over pi? We want to be able to solve that, right? All right, so let me move to the next screen because I think I've got another screen on here. Yeah. All right, so this is getting a little bit more into trig than we've actually dealt with so far. How in the world am I going to solve cosine of x equal to 2 over pi? Because that is not on the unit circle. Inverse trig functions. So, whoops. We can actually take the inverse cosine of both sides. So this is x equals inverse cosine, or cosine negative 1, or you might have heard it called arc cosine, depending on the trig class you had, of 2 over pi. Now, if you want an actual specific numerical value, like an approximation, just to give yourself a visual, your calculator can do that for you, right? We're not going to be able to find an exact for this. The exact is inverse cosine of 2 over pi. So grab your calculator, somebody, for me, and I want you to do inverse cosine of 2 over pi. Making sure you're in radians. You're not going to be in degrees ever for calculus. So radians is where your calculator needs to reside. What is roughly the inverse cosine of 2 over pi? It's a decimal point. Did you get one?
0.88.
It's about 0.88. So this is the rough estimate, somewhere between 0 and pi halves. And what is pi halves approximately? 1.57, yeah, 1.57 roughly. Okay, so we're looking at something about halfway, right? 0.88 is about halfway between 1 or between 0 and 1.57. We're roughly halfway. All right, so we're supposed to draw a graph too. That was part of the directions. The sine graph is much more in depth than what I'm going to draw, but I'm actually only supposed to draw the sine graph between what x values? 0 and pi over 2. So if I were to draw the sine graph further, it would look like this. Something anyway. Where, well, obviously 0 is the x-axis or the y-axis right here. Where does pi halves put me? What is it? Nope. Where will pi halves put me? Say that again for me, Sam. At the maximum. Pi halves should be at the y value of 1, right? So it should be at the maximum. So the graph that I've actually got is just this part of it. It's not a very exciting graph, that portion of it, right? It doesn't really look like sine even. But it's supposed to start at 0. It's supposed to end at the x value of pi halves, which is a y value of 1. And what this is saying is that if I were to draw the tangent line, the secant line between these, right, the slope line, that somewhere about halfway between, it's not exact, but here, this location is the inverse cosine of 2 over pi, roughly 0.88, which would be about right here. And the tangent line should look not like that. Let's try one more time, not like that. That's pretty close. Do you buy it?
I do.
Looks pretty reasonable, right? Your graph needs to look reasonable, all right? So your graph needs to be accurate enough that the sketch makes me believe that you really think those have the same slope. And they do, according to the algebra and the calculus that we've done before that. The graph is just a visual picture of the calculus and the algebra you've done. Okay, is everybody good with that? All right, we have a couple more theorems we're going to take a look at. Theorem 8.2 and Theorem 8.3, and if you printed off your notes at one point, you may just say Theorem 8.2 twice, because I realized there was a mistake and fixed it later, but it should say Theorem 8.2 first. So we have a function, it's continuous and differentiable. That should seem reasonable. We've already had those preliminary sort of hypotheses in the theorems before. And we've got a function that has two solutions, okay? So two solutions means it has two x-intercepts, yeah? So we've got a graph that crosses the x-axis twice. If that happens, then it will have a derivative of 0 at least once. Okay? So let me draw you a couple pictures of this so that you can see what this is actually telling you. And you're going to say, well, of course I believe that. I've known that for quite some time. I did that in algebra. And we actually see a theorem very similar to this in algebra. If you have a function that crosses the x-axis twice, at least one location between those two x values, you will have, that was not good, you will have a slope of 0. Right? Yeah. And it doesn't have to be, this says at least one solution, right? It doesn't have to be exactly one. You could have more than one solution. Let's say, for instance, your graph did something like this. Ooh, man. Isn't that exciting? So we have only two x-intercepts, right? I mean, there really are only two x-intercepts here, definitely. But there's more than one, right? It said I have at least one. It doesn't say I have to have only one. So the picture I've drawn has 3 locations where the derivative is 0. But this theorem ensures me that I will have at least one location the derivative is 0. Now, it's important to notice, and I haven't made mention of this too much on the problems before, I just said that it had to be true, that this idea of being continuous and differentiable matters. Let's say, for instance, this graph didn't look like, the very first graph didn't look like a parabola, but instead it looked like that absolute value curve where it has a sharp point at the top. You guys have seen me draw that curve before, right, where it looks like this. Well, if you had this going on, it would have two x-intercepts, right? I mean, in theory, yeah. But it would not have a derivative of 0, would it? No. And we have the same problem if it failed to be continuous. What if we had the graph that went like this? You got to jump. We still don't have a derivative of 0.
Because that's like you can't take derivatives of sharp curves.
Exactly. You can't take derivatives when they're sharp curves, and you can't take derivatives when you have a discontinuity. So both of those features of this theorem, like those hypotheses at the beginning, they really do matter. If it fails to have one of those, it very well could fail to end up having that derivative of 0 that we're wanting it to have. Okay, let's take a look at another theorem, very similar. This one, again, tells you have to have it continuous and differentiable. But this takes the last theorem and it generalizes it. Okay, so the last theorem said I had two solutions then the derivative has at least one location where it's 0, right? This one says if I have n solutions, then my derivative location will have at least n minus 1 solutions. So let me draw you a picture of something that's got, it won't have n because n's a generalized form of a number, of course. But I'm going to do one that has, we'll do 4. So I have 4 x-intercepts. Then this theorem is telling me if I have 4 solutions, that's 4 x-intercepts, I will have at least 3, because that would be n minus 1, 4 minus 1, 3 solutions where the derivative is 0, 3 places where the derivative is 0. Do I on this picture? Definitely do. Have 3 locations where the derivative is 0. They are at the peaks and the valleys of this curve. Okay. And I could take this picture and I could sort of shift it up, kind of like the last picture I had over here, the middle picture right there. And I could shift it up, and you could see that that at least really is an at least. It could be more, right? This one had 2 solutions, and all of a sudden I was supposed to have at least 1, and I actually had 3. So you could have more than the at least number, but that's the smallest number you could have. Okay, are you guys ready to see an application of where we're going to see this used or how we're going to use this? A problem that uses this. All right. This question says we're going to prove the following. We have a function, x to the 4th plus 6x squared minus 1, and we're supposed to show that it has exactly 2 solutions. Okay, now, there should be sort of a red flag go off in your mind that says that doesn't sound quite right. What about this is different than the last 2 theorems? That word exactly is different, isn't it? So why in the world does this say, or why in the world is that a problem? The theorem said what? At least, and this says exactly, which means we're going to use those theorems, but it's not going to be a direct thing that says, oh, look, it says at least. I mean, we can't just pull it straight through. So let me show you what we're going to do. The first thing we have to do on any of these problems, just like we did on the mean value theorem, Raleigh's theorem problems at the beginning, is we have to make sure we're talking about something that's continuous and differentiable. Is this? Yes. And why? Because it's a polynomial. Okay, so this is continuous, it's differentiable, and the reason is because it's a polynomial. Okay, grab your calculator just for fun. I would like for you to take a look at what this graph looks like roughly. It's a good, helpful step into thinking about whether or not parts of what are going on sort of visually make sense. So in your y equals, you can put in x to the 4th plus 6x minus 1. And I'd like to know roughly what the graph looks like that you're seeing. And you can just use a standard window. The 10 by 10 window will be sufficient. Right, what does the picture sort of look like? It isn't exactly what it looks like. What does it look like, though? Looks like a parabola. Now, it's not a parabola, is it, Jason? How do you know it's not? By the equation. Right. That x to the 4th means this is not a parabola, but it has a similar shape in this particular equation to a parabola. This is a parabola. Where does it look like it crosses the y-axis? Can you tell from your picture? Something below, negative, yeah, right? Something below the x-axis, isn't it, right? I don't care about an exact value, but at least this sort of looks like the picture. It looks like it's crossing beneath the x-axis. Okay, so this is a rough sketch. So does it look like it's reasonable to say that it has 2 solutions? Seems so, right? And so when I'm talking about solutions, it actually means solutions to this equation, and solutions are the same thing. I've used them interchangeably. Hopefully you're comfortable enough with that. These are x-intercepts we're talking about. It looks like it's got 2 x-intercepts. Now, we did submit that we put in the negative 10 to 10 window, didn't we? So we don't really know what's necessarily happening outside this window unless we zoomed out a whole bunch of times. And then we'd still have a limited window, right? We'd still be assuming what would happen outside of that particular window. So from a visual perspective, we don't have the whole picture here. But we've got what we think seems reasonable. Okay, so I'm going to jot down a little bit of what I just said. So this looks like, or this reasonably looks like, looks to have two solutions. Looks like it should have two solutions. We kind of like to make sure it doesn't have more, because that's kind of a problem, right? All of our stuff before in those theorems we had talked about things being at least. At least. Why isn't it more? Well, let's take a look. Let's suppose we had three solutions. All right, so this is back to the last theorem. Theorem 8.3 says that if we had three solutions, then what would have to be true about the derivative? The derivative would have to have at least two solutions. Okay? So we've assumed we have at least three solutions, or we have three solutions. More than two anyway. So what we would like to say then is that when we take the derivative, this is going to kind of result in a problem. So let's take our derivative. So we're going to give our function the name f of x so that we can work with it from a general standpoint. What is the derivative of this function? You guys are good at derivatives now. What do you have? 4x to the third. 12x. And that's it, right? And this theorem back here says that when I take that derivative and set it equal to 0, I should be able to find some solutions. And what I'd like to say is that I don't really have two solutions. Because if I don't have two solutions, then I would be messing up with that theorem. Because the theorem says that if I have three solutions to the original equation, the derivative should have at least two. Are you guys following with me? Sort of, I'm assuming something's true, and I'm going to fall into failing to make that happen. I'm looking for something to be what's called a contradiction. All right, so let's see what this is. How would you solve this equation if you were looking for where in the world is this equal to 0? What's that? Factor out an x. Can I factor out a 4x? Are you comfortable with that? Okay. So if I factor out a 4x, what's left? Okay, this is algebra, right? Factoring. Then what? Right, you said each factor equal to 0. So what do you get from the first one? 0. So that's one solution. Yay, we got one. What happens on this other one? Okay, so your algebra is doing pretty good if you're getting a square root of -3. But there's a problem with that square root of -3. It's imaginary numbers. And did you know that the calculus you're working with is only in the real number system for now? I know. Calculus with complex numbers is something you usually don't see until much, much later.
That sounds terrible.
I know. Yeah. Well, but we're not going to deal with it today. So the good news is that this part right here, it doesn't work. This one does not have a real solution. So there is no real number solution here. I don't mean no real solution as in one doesn't exist. I mean as in there's no real number solution. It's not a real number, yeah? What does this tell us? How many solutions did I have?
One.
There's only one solution here.
This is wrong.
So there's only one solution to f prime of x equals 0, which means that we could not have had three solutions to f of x, which was the premise that we started with up here. Suppose we had three solutions. We tried it. We said, okay, let's pretend we have three and see what happens. And we found out, we ran into a problem. We should have found, if we had three solutions, at least two solutions to the derivative equation equal to 0. And we only found one, which means the original premise where we started, like this is like science class. No, a lot of you guys are in science, right? You often will try to prove something's wrong by trying it and then seeing that it failed. That's what we did mathematically. We tried something and it failed, which means that the premise we had at the beginning, the hypothesis, was wrong. We do not have 3 solutions. There's one more thing to make mention of, though. We sort of glossed over the fact, how did we know, besides the picture, we believe it from the picture, I get that, but how do we know that we really even have 2 solutions? Right? We've eliminated the possibility of having more than 2. We know we don't have 3 solutions or 4 solutions because we only got the derivative to have 1 solution. But why do we know that we actually only have 2 solutions? Well, one way we can do that is we can actually think about that from the intermediate value theorem. So I know it's been a while since we've looked at that. I do have another screen. Let me use this screen. So my picture that we've been looking at looks something like this. Now, so you know from a visual perspective, at least from what you're seeing sketched here, that it should have 2 solutions, right? But you'd like to actually write down some verification for why that's the case. Why in the world do we know it has at least 2 solutions? So let's try this. We're going to try, and it doesn't have to necessarily be these numbers, but notice that somewhere on the left-hand side, the graph is positive. It's above the x-axis. And somewhere towards the middle of the graph, it's negative. It's below the x-axis. Agreed? Well, the intermediate value theorem says that when it's above the x-axis and then it's below the x-axis, if it was continuous already, somewhere it had to cross. Are you guys with me? So the easiest way to do this is to actually say, notice by the intermediate value theorem, we can test a couple of points. So there's nothing special about these points, but they're points that particularly, they do happen to work. So I'm going to test x equals -2 and x equals 0. I know x equals 0 will work. That's definitely along the y-axis, and I see that picture being beneath the x-axis, right?
Why are we choosing -2 and 0?
Well, I want to choose over here, Jason, some number up here and something that will give me something down here.
Okay.
So I'm choosing x equals 0 on purpose, for sure.
That makes sense.
But the x equals -2, just I want to make sure I'm far enough away that I'm actually above, and -2 actually works. If we had tried a number that didn't work, we just have to try something further away. Like let's say we put -2 into this and we still get a negative number out of this. Well, let's try -3 or -4 or -10 or something, and then we would be good to go. At -2, I think, though, works, so let's check it out. What if we put in -2 into this equation? Well, I have, whoops, -2 to the 4th plus 6 times -2 squared, and then -1. So if you guys will, plug that number in, what do you get? Hoping for a positive. What do you get? 39? Is that what you said, Ben? It is 39. Good. This is 39. And let's plug in f of x, or I'm sorry, plug in x equals 0. I don't think you really need to put that one in your calculator. Just a thought. What do you get? -1. Right? Get -1. So somewhere between -2 and 0, f of x equals 0. It crosses the x-axis, right? Because -2, we're above the x-axis at 39, and at 0, we are below the x-axis at -1. So somewhere between those values, it definitely had to cross the x-axis. So that's one of our solutions for sure. But we can do the second solution for the same thing. We can do f of 0, and then let's do f of 2. And if I plug those numbers in again, I actually am going to get -1 and 39 again, because when I was actually squaring and powering for those values, the negatives canceled, right? Yeah.
So, what would our answer be to that question? All of this?
Yep. So somewhere, we'll write up something here in just a second. Somewhere between 0 and 2, f of x equals 0 again. All right, so this is a very good question, Taylor. We've done a lot of work. What in the world of this work is the actual answer to what's going on? And to some extent, yes, the answer is all of it. So a couple of things to remind us of where we've been and what we actually did is we need to make sure there's really 2 solutions, right? which means we can't have more than 2 and we can't have fewer than 2. Agreed? So we started out with a graph to see, does it really make sense that there might be true? And we said, yep, looks like so. Looks like from the graph we've probably got the 2 solutions. Let's make sure there isn't more. So by theorem 8.3, that was actually the theorem we used because we were using n equal to 3 or 4 depending on the number of the solutions we were looking at. So by theorem 8.3, we know there are not more than 2 solutions. That's what we used theorem 8.3 to tell us, is that we actually went through that and we said, okay, let's pretend like we have 3 solutions and see what happens. And we found out it didn't work. Okay? And by the intermediate value theorem, we know there are at least 2 solutions, because we saw that, right? That's the work that's on the bottom of this particular screen right now. So if you can't have more than 2, and you must have at least 2, how many solutions do you have? 2, right? I mean, this is it. So there must be exactly 2 solutions. We showed that there couldn't be more than 2. We showed that there couldn't be less than 2. So it must be 2. All right, we have one more problem to take a look at. This problem is an application of what we're working on. It's a very valuable piece of information, and it's going to generate for us some guidelines that we've talked about sort of in passing, but we've never written down as such before. This question says to determine whether the function is increasing, decreasing, or neither, and the function looks an awful lot like the function I just had on the previous screen. The only difference is the coefficients actually that are there. I've got a 4th power, I've got a squared power. So I'm not terribly concerned that this be a difficult derivative to find. I want to show you the application of the increasing, decreasing business. So when we were looking at graphs before, we've done a lot with tangent lines, right? And you guys know that the tangent line is 0 when it's horizontal, right? The tangent line slope, the derivative of the graph is 0 when the tangent line is a horizontal line. What happens, or what can you tell me, when the tangent line has a positive slope? What does the graph look like when the tangent line has a positive slope? Can you picture it? What would the graph be doing if the tangent line slope is positive? Increasing. So we're going to jot these things down here because this is very important information for being able to answer this question. So when the graph is increasing, this is a two-way correlation. If you have an increasing graph, then the slope of the tangent line is positive. It's a positive number. And remember, phrase slope of the tangent line is equivalent to what phrase? Derivative. So if we are looking for when the graph is increasing, we could equivalently be looking for when the derivative is positive. Because if the derivative is positive, then the slope of the tangent line is positive. A positive tangent line slope means the graph's increasing. All right, so let's just throw it out here. What happens if the graph's decreasing? Right, if you have a decreasing graph, this will happen, again, this is a two-way correlation or a two-way statement. This will happen when the slope of the tangent line is negative, not decreasing, it's negative. When you have a negative slope, you'll have a decreasing graph. And a negative, and a tangent line is the same as talking about the derivative in this phrase. So when I'm asked to find if the function is increasing, decreasing, or neither, this is equivalently asking me what to find whether the derivative is positive or negative or neither. But now think with me for a moment. What is neither going to mean? 0. So what I'm really looking for is I'm looking for where the derivative is positive, negative, or 0. So these directions, write yourself a note because this is really important and we're going to see it come up a lot more in Chapter 3. I know you don't want to move to Chapter 3 yet, but we will be very soon. This idea right here is equivalent to talking about the derivative being positive, negative, or 0. So if that's what we're really looking for in this equation or this question, we better find the derivative. Agreed? So let's take the derivative. What is the derivative of this equation? Okay. Okay, so now it's going to feel like something you've done in algebra, and depending on how recently algebra was, will depend on whether you remember it or not. What we're going to do is we're going to set this equal to 0, and we're going to factor. Because one of the issues is where the derivative is 0. That's the easiest one to find. So we've factored something similar to this just a little bit ago. What can I factor out of both pieces? 4x, and it factors out with what left over? X squared plus 1. Okay, so we set each part equal to 0, just like we did on the problem before, right? What happens? The first one's going to be 0, right? Yeah? And then what happens on the second one, Kieran? Is it?
Plus or minus the square root of negative 1.
Ah, it's the square root of a negative, because when I move this 1 to the other side, it's going to be negative. Another way to think about this without dealing with the imaginary number bit is to take a look at this. Can I put a number into x squared, add 1 to it, and never get back to 0? Not in the real numbers, I can't. Right? Any number I put in I square it, it's going to be a positive number, right? And if you add something else to that, a positive number, it's going to still be positive. This can never be equal to 0 in the real number system. I'm almost done. I know we're about out of time. So this doesn't give me any answers. Here's what we do. This is the last thing we do to make the decision. This is the part that would feel like algebra. You set up a number line, and on your number line you put in the x value or values that you have. This is x equals 0. Okay? That's the only value we have. If we had more than one value, we would do that. You pick a test point. So it doesn't matter what test point. Make it something easy to work with. I like the number 1. It's a great number, because it's easy to plug into what's going on. You test it into the derivative. If I put in negative 1 into this derivative, what do I get? Okay, my question, let me rephrase. Do I get a positive number or a negative number when I plug in x equal negative 1? A negative number. Because f prime of negative 1 is negative. What if I plug in a positive 1? I get a positive number. So here's the answer to the question right there on that picture. That number line answers the question.
Did you plug it in before x cubed plus 4?
Mm-hmm. Into the derivative, yes. Here's the answer to the question. I know you guys have to go. My intervals went from negative infinity to 0 and from 0 to infinity. It was negative slope before 0. This is a negative slope, right? That's not part of the answer, but that's what we recognize. This means that the function is doing what? Decreasing. You got it, Mandy. And from 0 to infinity, the right-hand side of that picture, my positive slope was going on, and my function was increasing. And that was what I was asked to find.